supermassive black holes and all that. He has done so much work in galaxies, galactic structure, so we look forward to his talk.
Good morning. I'm very happy to be here at noon today, giving a talk in this symposium in honor of Chandra. I'm very grateful to the organizers for inviting me here, but I don't think I completely agree with their scheduling, because there have been these two magnificent talks on quantum cosmology, and suddenly you ask me to talk on galaxies. And it is not as if I'm going to be talking about marvelous things about formation of galaxies and so on. I'm just going to be talking about rather poor analysis of systems which are not very well understood, poor data, speculation, omission of points which are not convenient to the statistics, okay, and then making wild allegations. Okay, so I think that this is completely out of tune with what went on in the morning. Rather, they should have introduced some theoretical astrophysics gently, and then got you used to it, and then people like me should have been here on the stage. But anyhow, I'm going to be talking to you about the morphological properties of galaxies here. So there are all sorts of galaxies. I'd be today referring mainly to lenticular galaxies. So this is work which I've done with a number of young people over the years, and without them the work would not have been there, particularly in the later years. Okay, these the people who have worked with me as students and postdocs, or in the later years mainly worked with each other. And they're all now well settled in various places all over the world. So now let me begin with Hubble's tuning fork. Now this is a diagram which those of you who have studied astronomy at all would have seen many times. It was made through observations in the late 1920s by Hubble, who studied galaxies, of which there is a bewildering variety, and he did what botanists and zoologists and generally people working on life sciences had done over the preceding 200 centuries, where you look at objects which appear to be so different from each other and try to find some common properties and try to put them together, so that the understanding is passed from the impossibly difficult individual objects to classes. Okay, and then the next step would be to see how classes are related and how and whether there is an evolutionary sequence, so that in the initial act of creation of these objects you just make a few different kinds, and these through nature and nurture, and that is through their own dynamical evolution as well as from perturbations which they receive from outside, change into this variety that we see now. Okay, so that is principally the goal of all observational sciences, where we first try to order through the observations and then through the understanding. So there are these, now each one of these objects, these are all these classical objects which are in our neighborhood relatively speaking. Now each one of these objects contains 10 to the 11 to 10 to the 12 stars. So it is the light that you see from these objects is primarily from the stars. There's a little bit of gas in between. And then they could also be supermassive black holes. Right, so now there are these galaxies that appear to be fundamentally of different kinds. So first you have got the ellipticals, which come to the left of the diagram on the stem. And these objects are relatively simple to look at. I mean, there are a large number of relatively old stars, and then the objects seem to be dynamically relaxed. Okay, so they have this elliptical shape. It was believed initially that the ellipticity is because of rotation, but we know now that it's because of anisotropic velocity distributions, because the galaxies simply don't rotate fast enough to produce the flattening observed. So these galaxies contain not very much gas, and it was believed that they're completely devoid of it, except that X-ray observations, they emit X-rays copiously, which means that even though they're lacking in cold gases, they've got hot gases in them. They're very interesting to study dynamically because of the simplicity to see how these objects form and evolve. And many of these objects, though probably not all, most certainly not all, were quite old, and they were just formed in the initial stages of the universe, and then they evolved passively. Okay, meaning that you form stars and just leave them So the evolution comes from the aging of the stars rather than anything else. But on the other hand, we also now know that if there are major mergers, which means that if major galaxies come together, collide and mix, then what would happen is that they bloat up the matter distribution in the velocity space so that you get an elliptical galaxy like this. So some at least, many in fact would have been formed through interactions in relatively recent times. Okay, then even though they are completely, they appear to be rather quiet and featureless objects, the fact that they are very massive, okay, means that they are correlated with large black holes. So you could have supermassive black holes in them, and these become through the accretion of matter, so that they shine up as quasars. So for example, all radio galaxies are associated with elliptical galaxies. So even though these objects appear to be simple, they can have very complex features when they are observed with sufficient resolution and observed at different wavelengths. Now this object, for example, M87, was right from the beginning of the last century, was known to have a jet in it, and now we associate it with spectacular radio structures, superluminal motion, and every kind of activity that you can imagine. So then come the spiral galaxies. Okay, so when you move to the left of to the right of the diagram, and this is the general amateur astronomer's perception of a galaxy. It's a grand design spiral. So you've got these very spectacular spiral arms. Now this is essentially a flat object. There's a flat disk, and then there's a bulge in the center, and you're looking at it face on. Right. So the big difference between a galaxy like this and the elliptical galaxies is that these contain gas. So there's a great deal of star formation going on. Then there are the spiral arms. The disk rotates. And these are very active in that sense, in the sense of having a lot of star formation going on, matter being recycled through stars. Okay, but on the other hand, the larger supermassive black holes and the AGN-related activity is louder in the apparently quiet elliptical galaxies. Okay, then right at the junction of the two arms, then you have got these objects which are known as transition objects. Okay. So these are the lenticular galaxies, and this is a very nice picture taken by Barbe. So these objects, they have, unlike the elliptical, they have a disk. But unlike the spirals, the disks are lacking in spiral arms. Okay, so you are going to rather, in that sense, these are very boring objects because the bulges are not as spectacularly important as in the case of elliptical galaxies, but you've got a disk which does not seem to have much happening in it. Okay, but these objects are very interesting from the point of view of formation mechanisms and how did these objects form? I mean, are these just spiral galaxies from which stars have been stripped, okay, or were these formed in this way initially? And is this a homogeneous group? Okay, meaning that could we have objects which look like lenticulars, and if you just classify them on the basis of their visual appearance, then you might classify them all together, but they could be fundamentally different from the point of view of formation mechanisms. So what I'm going to be doing today during the course of my talk is actually to look at some very simple correlations between parameters which define the large-scale shapes of galaxies like this, to try to see whether one can get an idea about their formation mechanisms. So now, as I've already said, these lenticular galaxies are in many ways, in most ways, intermediate to ellipticals and spirals, right? So that if you look at any property of these galaxies, like for example, the bulge to disk ratio, okay, meaning that an elliptical galaxy can have small, but the disks are not very important. Okay, the luminosity is negligible compared to the luminosity of the bulge. A spiral galaxy, on the other hand, has got a very significant disk, and as you go towards the later irregular spirals, the disk can become completely dominant and the bulge can vanish, in fact. Whereas in the case of a lenticular galaxy, this ratio is like half. Okay, so half luminosity, let us say, in the bulge and half in the disk. And then in every other thing, meaning that if you look at how much molecular gas is there or what is the mass to light ratio of the galaxies, they are very intermediate. Okay, so that, which is why Hubble believed there is a transition class, and as ellipticals and spirals cross from one kind to the other, they could do that through the intermediary of a lenticular galaxy. Right, so now I just want to give you a little bit of quantitative detail on how one actually looks at the large scale morphology of these galaxies. So if you look at this one, which is I choose it because it is a completely featureless, very simple elliptical galaxy. And then it's called an elliptical galaxy because the isophores appear to be ellipses. So if you just look at the constant intensity curves there, which we call isophores, you see that they're all elliptical in shape. Now there can be all kinds of complications here, and we have got if you take a typical isophore, then there's a major axis and a minor axis which defines the ellipticity. So the ellipticity here appears to be quite constant, except when you come to the center where the isophores appear to be becoming circular, is more because of the point spread function, the spreading of the light of the galaxy because of the turbulence in the atmosphere, okay, rather than being a real effect. So, but in a more complex structure, you could have the ellipticity turning from changing as you go from the inside to the outside. It could increase, decrease, go through a maximum or whatever. The ellipses could all rotate relative to each other, okay, meaning that you could have the major axis in this direction for one isophore and the other direction for another isophore. So the question is, what are the kind of three-dimensional shapes that these objects have? So as I said, the most natural shape would be where you start with a spheroid and then spherical shape, and you rotate it and you get an oblate spheroid. I mean, many of these galaxies are infinite, but the shape is not because of rotation, rather it is because of anisotropic velocity distributions. Okay, then most of these galaxies are oblate spheroid, but a few are known to be prolate, and the ones which are oblate actually could be triaxial. Okay, but to actually work out mathematically the shape, the three-dimensional shapes of these objects using photometric data and spectroscopic data is extremely difficult, and that's a big thing in itself. So now, having looked at these isophores here, it's obvious that the intensity would go down as you go along the major axis in this case. So the question is there any order? Is there any simple way that the intensity falls off? So now this was again done by the early observers, the Dvořák's. So these people collected data on literally thousands of these galaxies. They had to all principally do it with the eye using photographic plate. Then they made very simple measurements, and then they looked at for example, in NGC 661, you have got the points and you see that they very clearly lie on this very simple curve here. So this is a plot of the average surface brightness on the isophore as a function of 1/4 of the distance, 1/4 power of the distance. So why do we take this power? Simply because the Dvořák's got a straight line here. So as you go in, it seems to bend over, but that is mostly due to it is here in this particular galaxy. It's again because of the spreading of the light, what's called the point spread function, as the reason because the light gets more spread out. Right. On the other hand, if you this kind of, it's very important actually to get an idea about whether indeed it's an effect which is completely determined by the seeing, or the real flattening of the curve. That is because, I mean, theoretically, this simple law which the Dvořák's gave, R to the quarter law, the rate of change of the intensity would become infinitely large as you go in there. But what there must be some change in that, and then the question is whether the galaxy has got a core. And if it has got a core, then there will be a bending of the intensity profile. Now, in addition to all the stars which define the core, let us suppose that there is a supermassive black hole sitting at the center. Then that would perturb the orbits of stars around it, and we should have some discernible effect on the distribution of light, the kind of distribution that I am talking about here. Okay, so the question is, how can you separate out the effects of the atmosphere from small effects which are there because of the presence of a possible supermassive black hole? Okay, so this kind of a thing can become extremely important. Right, so I mean, needless to say, not all galaxies would produce such a good fit, and you need some generalization. So generally, you take a point source at the center, which is the active galactic nucleus, and then the bulge and the disk. These are the Davoculus bulges, but a very simple generalization is where you replace 1/4 by 1 by n, and you keep n as a free parameter. Where the disk itself, for a very long time, since the early 1960s, has been parameterized as an exponential. Okay, so the distribution of light is exponential, and the orbits of the star are, and you can make them elliptical or whatever, but it doesn't make much of a difference. So now you see that here are a number of real galaxies for which we have looked at the intensity profiles, and then you see here that these are different values of n. So it's clear that when you introduce an extra parameter which controls the shape of the intensity profile, then you are going to get better fits. But then the extra parameter becomes important if it shows interesting correlations with other galaxy parameters, because then one could use it to get some idea about, to classify galaxies or even to talk about how they were formed. So this so-called Cercic parameter, therefore, has become quite important, and you no longer treat galaxies as Davoculus objects, but as Cercic objects. So now again some words on how do you actually determine these things, because what Davoculus did, he just looked at the fall in the intensity, just averaged in some very crude way, and then just plotted it and got the 1/4 law. So the important thing was that he did this for thousands of galaxies, and then there are these enormously large catalogs that he and his students and other co-workers produced over the years. But what we need to do now is to find better and more stable ways of actually looking at the fits. So what you do is that for this particular galaxy, which is just chosen at random, what happens is that these are the isophores that you need to fit, and you can very clearly see that this is not quite elliptical. It's as if it has got an edge to it, this isophore, and that is because of a disk that you are looking at. The disk of the galaxy is flat. So if you look at it face on, you'll just see a circle there like I showed you in the case of M57, but if you look at it sideways, then you'll see an edge there. Right, so now you want to fit this. So the way we go about it in these modern times is that you take, this is a CCD image, you've got the two-dimensional data. So you make your galaxy, make a model of the galaxy with a point source, which is not usually done. You're with a bulge and a disk, and then you take that model and then you convert it with the seeing function. Okay, and then you get a trial figure which you impose on top of the observed figure, and just do a chi-square analysis like this. Just minimize chi-square by varying the parameters. Now this can be pretty dangerous actually, because if you have got a simple elliptical, there is no problem at all. But if you have got an elliptical, a bulge and a disk, then you are talking of 3 or 4 parameters. And then on top of that, if you go into the real shapes of these galaxies, okay, meaning that look at a spiral and then you just see whether you put in a spiral you try to put a bar, or you try to put in spiral arms and so forth, then you will really have lots and lots of parameters. So now if you can imagine a multidimensional parameter space, there will be all kinds of minima lurking here and there. Right? So you can get completely wrong solutions. So how do you know that you've got a wrong solution? You really can't know that. What you need to do is to look for minima, then perturb the parameters and so on. And then you look at the curves. Even if you get, the eye shows you've got a good fit, they may not be true. So all this uncertainty actually goes into the uncertainty related to the results that you get out of these objects. Right? So in my experience, it is virtually impossible for a given object to reproduce the parameters found by anyone else. Right? Because if I change the parameters, the errors in the parameters are very highly correlated. Okay, so you can't really reconstruct somebody else's solution. But what happens is that we go by the statistics, meaning that if two people analyze 100 galaxies and they look at certain distributions, the distributions agree largely with each other, and your physical conclusions are based on the distribution, there's not much to worry. Okay, but if you're talking of individual galaxies, then you have to be very careful. And because there are all these wonderful computer programs which are already available, some developed by us, some developed by other people in the industry, meaning the astronomical industry. So then those can be used pretty easily now, and which leads to an enormous number of papers which make it to the archives. never anywhere else. Okay. So here is another, just for fun, here's another nice galaxy here. Now, unlike the objects which I'll be talking about today, these are non-local. It is a redshift of 0.55. So you can't get an image like this with a terrestrial telescope because of the seeing. This is a Hubble Space Telescope image. Okay, and then the same programs have been applied to it by Abhishek Rawat, and then you see a very nice smooth galaxy here. And the parameters of these galaxies will go into the physical considerations, but you have to always be aware of the fact that when you subtract this smooth model from the original observed galaxy, then you see these clear spiral arms which are standing out. Okay, so this is very good for actually talking about the spiral arms, but it is not necessarily very good for using these parameters in the subsequent analysis. Right. Okay, so now what kind of correlations are we talking about? Right, so there have been lots of them. People have been plotting all sorts of things and all sorts of other things, because once you make a big catalog, that's a normal thing to do. But a very important correlation is what is known as the fundamental plane. Now, this was discovered by two groups simultaneously in the 1980s, and what happens here is that this is a parameter which is called the effective radius. So basically, it tells you the radius of the object. You can say from the center within which half the light is included. Okay, so that is the radius there, and what you would like to do is that you want to know the radius in which the whole of the light is included, and unfortunately that's not a well-defined quantity. Okay, that's because the light from the galaxy gradually tapers into the sky. Right, so therefore what you really want to do, so therefore this parameter becomes more stable. Okay, then here you have got the average intensity of the galaxy within this RE, and these are what are called photometric parameters. Okay, meaning that I take an image of the galaxy, I could do it at a single wavelength, or typically it is in a broadband, and I get these parameters. On the other hand, it's a dynamical parameter. Okay, though it is actually the average dispersion velocity of the stars close to the center of the galaxy. So this is a very loaded kind of definition, because what do you mean close to the center of the galaxy? What kind of an aperture that I use? So if I take a large galaxy and then I use an aperture, put it around the center of the galaxy, then a certain linear size of the galaxy will be covered by that aperture. Now, as the galaxy recedes into the distance, then I am taking in a different linear size. Okay, so which means that I could be talking of one starts with one galaxy and another group of stars with other galaxies. So you need to apply corrections all over the place. Right. So, but then what is very interesting is that this is a logical parameter, and what you get is this one which is known as the fundamental plane. The idea is that you could correlate. There are three parameters involved. You could correlate them against each other, and those correlations are well known, and they are done over the years. For example, there's a Faber-Jackson relation which contains the luminosity to sigma here, right? But then those parameters, those correlations all have large dispersions in them, and what was discovered by Jergowski, Davis, and the group which is known as the Seven Samurai was that when you plot them in this particular combination, you get this very tight correlation. Right? So what is happening here is that you can imagine the three canonical axes for the parameters, which is I, sigma, and Re, and in that axis you've got a plane. So now, in order to make that plane discernible here, what you do is that you look at the plane edge and you make a plot here. Right? So if objects indeed are spread out over a plane, if you look at it from the top, okay, then you will see the objects scattered all over. You will not see any relationship at all. But when you look at it from the side, you see them all along a straight line. Okay, so that is what is being done here. Now, the point is that you look at the scatter about this line, and these are essentially elliptical galaxies. You look at the scatter about this line, and the scatter is rather tight. So now how you define the tightness is by comparing the scatter with the error in individual points. And then you find actually, as the observations improved, people found that the scatter is, that the scatter around the plane is consistent with the errors, meaning that there is no other effect. Meaning that if you, let's say, made a plot of IE against sigma, you will find a lot of scatter in just a two-dimensional correlation. And that tells you that there must be a third parameter lurking. Right? So, but when you plot these three, it seems that it is finished, and which is why there are, you call it the fundamental plane. So now, why should you get this plane and what implications does it have? Is that if you now actually look at, if you look at the virial theorem, okay, which connects the total gravitational energy with the mass and the size of the distribution of the mass, okay, then you would get a relationship which is like this in this plane. Okay, but the normal to the virial plane is tilted relative to the normal to the fundamental plane. Okay, so why this happens, why there is this tilt is not completely well understood, but it imposes conditions on the mass to light ratio of the galaxies. Okay, so which all becomes very interesting because what happens is that the light is coming from the individual stars. Okay, there's some parameters that you are talking about here. These parameters define the overall morphological structure of the galaxy. So what you are getting now a relationship between galaxy morphology and the stellar content of the galaxy. Okay, so which can give a lot of insights into the fundamental nature of the galaxies. Right. So now the fact that the scatter is so small, it means basically you say that is because elliptical galaxies are well settled objects. Okay, so they were created a long time ago, either primordially or through interactions between major galaxies, and then they have had time to settle down, they have had time to virialize, and so in some manner every point drops onto the plane. So now the question is whether there are other kinds of galaxies which should be away from the plane. Okay, so people used to say, you could imagine here that always they are resting on the plane. But on the other hand, what has also been found is that you could have relatively recently, meaning like about 1 billion years ago or so, you could have major galaxies which are interacting with each other, which again quickly seem to settle to the plane. Okay, so then you could now look at different kinds of objects. For example, you can look at ellipticals and lenticulars, they are all in the same plane. Then you can look at bulges or spiral galaxies and all that. And you find occasionally that there is the spread increases. Okay, and the hope is that you will be able to calculate in some fundamental way what is happening to the galaxies and how they settle onto the plane. Now, needless to say, there are many different ways of looking at this kind of an idea. Now, one of the things which is involved in the fundamental plane is that one parameter, that is the dispersion velocity, is spectroscopic in nature. And so you could ask yourself, can one do only with photometric parameters? Okay, because photometric parameters involve just the images of the galaxies, can even be obtained by a small telescope. You don't require really large telescopes to do these kind of observations, but spectroscopy requires either you point to an object and you get the spectrum at the center, okay, or you use very sophisticated equipment and you get the spectra of objects which are several objects, many hundreds of objects sometimes, which are in a small field of view. Right? So all that becomes very time consuming. So it is good to try to simply look at correlations between these parameters here. So what you find is that here, for example, is the surface brightness. I mean, we are always talking about a measure of the surface brightness, the average surface brightness, the different measures used by different people, and a measure of the spreading of light, which comes from a scale factor there. Okay, and then n here, the Cercic parameter, which tells you what shape the galaxy profile has. Because if it is always equal to 1/4, I simply have r to the 1/4 along my axis, then it just becomes a straight line. But if I make a r to the 1/4 plot for an object which has got n is equal to 5, then you will get curvature there. Right? So therefore, you require a parameter like this. So now, if you look at these correlations like this, I mean, I will not belabor you with these the details of this, but this is what's called a Kormandi plot, And then you find that the elliptical galaxies are here fairly nicely settled here, but the bulges of these other bulges of galaxies, spiral galaxies, they seem to fall down from that correlation. Okay, so again, the fact that there are two allows you to combine them together into what is known as the photometric plane. Okay, so you see that this looks very much like the fundamental plane, except that it is based entirely on photometric parameters, which has its advantages, as I already said. And moreover, it unifies the bulges of spiral galaxies, okay, with elliptical galaxies. Okay, so these are unified together, they all seem to sit together. But that's because I'm looking at the plane edgewise. If I now looked at the plane from the top, okay, then you would see all these points spread out. Okay, and then now what your theory is going to have to do, your modeling, is to look at the spread of the parameters, how much the bulges are separated from the ellipticals, and that will tell you about how they are related to each other. Right? So now again, we have been looking at these kind of correlations in a series of papers, mainly with Sudhanshu Barve, who is now at the South African Astronomical Observatory. He just goes on doing all this work. Here the idea is, now you come back to lenticular galaxies. So when you have the ellipticals either were born as they are and have been evolving passively, or they were created in the mergers of major, what are called major mergers. Okay, which means that objects, large objects which have more or less comparable mass, which are merging together. Okay, on the other hand, if you look at a picture of the Andromeda galaxy, you find that there are several dwarf companions around it, and these dwarf companions could in the course of time be swallowed, and they also allow the galaxy to change its shape. Okay, those would be called minor mergers. Okay, so elliptical galaxies were born in major mergers, let us say, if they are not born primordially, and whereas the spiral galaxies, so you've got a bulge there, so you could first form the disk, you form the stars in the disk, okay, then you develop a bar in the disk, and that bar pumps in gas and stars towards the center, which bloat up. Okay, so then you get a bulge. So now if I therefore present you with an object which is not quite an elliptical nor a spiral, okay, then it has got a bulge and a disk which are comparable. The question is, how was this object formed? Okay, was it formed as it is, or whether the bulge can be ascribed to bars? A bar is not a long-lived phenomenon. What happens is that a bar develops in the galaxy, and then it pushes in the gas, which sort of starts having a bulge, which disrupts the bar. But after some time, again a bar is born. So there could be several of these bar episodes which form the lenticulars. Okay, so then are the lenticulars primordial, or are they formed through the bars? So you see that here we have got a set of lenticulars are observed, 35, and these are observed with a Mexican telescope. The thing is that carrying out these observations over a period of time, etc., it's very time consuming. Okay, so you might imagine that with all the modern technology, we can simply do that in a couple of evenings. But you can't really do that because you normally don't get access to the most modern technology for carrying out work like this. Okay, so when you want to do surface brightness of bright galaxies, you have got to depend upon smaller telescopes. Like 2 meters is quite enough. Okay, but mostly it is raining when you try to use the telescope, and it just goes on like that. Okay, so it takes a long time. So whereas if you use archival data, one could work with tens of thousands of galaxies just like that. But if you are basing it on observations, okay, then you have to work with smaller numbers. So here is this set of galaxies observed, and then what these other people did was that they took a suitably defined set of objects and got 2-mass data. 2-mass is a near infrared survey which covers the whole sky. So basically, you can find the image of every galaxy in it. The only problem is that the exposures are relatively short, as a result of which you can only do certain kinds of problems with bright galaxies, not everything. Okay, so when you now, as it happens, these objects here are bright. Okay, meaning that here is the absolute magnitude, and the more negative the absolute magnitude, the brighter is the galaxy. Okay, so you see that here is a bright set of galaxies, and then here is a fainter set. So, and these are bright and faint, not in terms of their appearance, but in terms of their absolute luminosities, the amount of energies that they emit. Okay, so what we do is that we try to correlate the effective radius of the bulge against the disk scale length. Okay, so you get this correlation, and then we have developed this wonderful software. What it allows you to do is that, oh my God, this correlation is so nice, but just get rid of these 3 points. You can just drag them and drop them away. Okay? No one knows anything. I mean, I was very proud of having developed such a thing, okay? But I realized that it would be something which is very disruptive. Okay? So you see that here are the 3 outliers, and if I drop these 3 outliers, then I get this wonderful correlation here. So why drop these outliers? Okay? So that is where you become very optimistic. What you do is that you see that it is somebody else's sample, you are using their parameters. Then you actually go and look at the images, and in all these 3 cases you will find that these galaxies are very ill-defined. Okay, so all this putting in the isoforts and getting the elliptical shapes, etc., is quite nice, so long as there is not another big galaxy within sight. Okay, because then even though they may not be interacting, they may be at vast distances along the line of sight from each other, but still the isoforts can perturb each other. So and when the isoforts perturb each other, if you are not noticed that, and typically if you are running a pipeline, and that is what we all do now, just run a pipeline, go for tea, and you get the galaxy analyzed. Okay, but then it can turn out that your analysis is wrong. So these are all objects which are terribly deformed. So we are very happy with this correlation. Now look at this other set of galaxies. So what is this? These are the faint lenticulars and these are the bright lenticulars. So now in this other set of galaxies, there is clearly a nice correlation here, and which would really lead to a paper because these are positive, this is negative. But then what do we do with these points? Okay, so that's the question. Then you see, now this has been developed over a series of papers, and I'm just presenting it as something which has been done. So you see that these points which are there, now these are all beasts of a completely different kind, meaning that this is the kind of number that you require for lenticular galaxies. I told you that in lenticular galaxies, the bulge occupies about half the total luminosity of the galaxy. They are more or less comparable. And what do you find here? You find here that the ratio is much low. It's more appropriate for spirals. Okay, so you are really comparing different kinds of objects here. So you isolate the lenticulars like this, and then you see that clearly you have a nice one set of them. The less luminous lenticulars have got a positive correlation, and the more luminous lenticulars have got a negative correlation. So how do we do this now? So we just mix all the objects together, and then you see that it becomes clearly a luminosity dependent effect. Okay, so what happens is that now in the case of the less luminous lenticulars, where you got a positive correlation, what happens there is that it means that the bigger the disk, the more there is the matter in the disk, the bigger is the bulge, right? So you see that you first build the disk, okay, then you develop a bar, and then you pump gas and stars toward the center, right? So then you build the bulge like that, and from the modeling you know that requires a positive correlation. The negative correlation is anticipated when you got mergers. So which means that there appear to be 2 different mechanisms for the formation of these lenticulars, where you get one kind is born, the low luminosity ones are born in one way and the high luminosity in the other. Now there are any number of correlations that I will not drive you mad with by describing to you. Okay, so where you try to move this idea forward. Okay, but I'll just show you 1 or 2 important ones where this is again very recent work, paper just published. Okay, where if I claim that the less luminous lenticulars depend on bars for creating bulges in them, okay, then there should be correlations with bars. Okay, meaning that I should find bars more often in the lenticulars, and which is what you find. And so these are the here are the more luminous ones. I compared you see that this is the overall distribution of lenticulars. Now this is the dividing line. Now the dividing line is not completely arbitrary, you can move it up and down, and it is very carefully chosen. Okay, and then you find that the faint ones have bars much more often than the bright ones. Okay, so all of which is consistent, and then you see here, I just want to show you something, and this is very, very fresh, probably wrong. It just came by email last night. Okay, so there what you try to do again, the idea here is that I should be able to substantiate the fact that some bulges are old and some bulges are young, right? So how do you do that? Because those bulges should have different colors. So what do I mean by old and young is that the stellar populations be quite different from each other. So the younger the stars are, the bluer they are. Okay, so it should be possible. What has been done here for a large set of lenticular galaxies? So here we plot. So this is the observation at a visual wavelength. This is the observation of near infrared wavelength, and this is at extreme ultraviolet. Okay, so now these are what are called color diagrams, and then objects which have intrinsically different colors would belong to different parts of this diagram. Okay, and then just by looking at one color diagram, you cannot say much, but just imagine that an object has been observed at many different wavelengths, and again you can imagine a multidimensional color space. And what one can do is that one can consider models of the stellar populations in the galaxy, what kind of stars there are as a function of the mass, how many of them are being born now, and then you could then you could use these large stellar libraries to predict the colors of these galaxies and see where they would lie in this multidimensional space. Okay, and it is extremely important for you to develop a proper sense of how the stellar modeling for you to be able to justify the different formation mechanisms now which is on its way. So now in the last few minutes of my talk, I want to consider correlations, this kind of morphological correlations, but bringing in a completely new element which is a supermassive black hole. Okay, so I mentioned that once or twice, and now when quasars were first discovered, and then when people also found that objects like Seyfert galaxies and radio galaxies have quasar-like properties, then you have to find the source for this immense amount of energy which comes out from the center of the galaxy. The characteristics are, the emission is truly multi-wavelength. Okay, meaning that if you look at the sun, it emits essentially at optical, near infrared and ultraviolet wavelengths. It emits at X-rays, but there's a small, very insignificant fraction of the total energy emitted by the sun. On the other hand, when you've got a quasar, and you look at the luminosity at any wavelength nearly, and you will find it the same. Meaning as the technology develops, you go from the radio, you've got the infrared, near infrared, visual, then you've got ultraviolet, X-ray, gamma ray, and then you've got all these TeV emissions. And at every wavelength, you've got the same great deal of energy which is coming in. Okay, which means that there are many different mechanisms which are operating, all of which have to be understood to get a full idea about the nature of a quasar. Okay, so now the quasar light is emitted from a very compact region, and the region is very compact, and it has got relativistic motions occurring within that region. Okay, meaning that there are macroscopic, there are large clouds of gas which are moving at relativistic speeds. The consequence is that you actually see superluminal motions, and then you see all kinds of other phenomena which are related with very large amounts of matter moving at relativistic speeds, which tells you that there is an extremely deep potential well there, and which leads you to believe that there must be a rather compact object sitting there. Now the question is, it is just a compact object in the sense of being, for example, a very large collection of collapsed stars. Okay, so could I have 10 to the 9 stars going around the center of the galaxy, providing the gravitational potential well, which leads to all this phenomena. Now it turns out that nothing works, and you are inexorably led towards a completely collapsed object at the center. Okay, so you have got a supermassive black hole. So now if I see these supermassive black holes in quasars, the question is, are there such black holes at the centers of all galaxies? Some of them at different times. So that at any given moment, only a small fraction of the galaxies have these special properties. Right? So one way of trying to understand this further is to actually try to see whether there are these supermassive black holes in completely ordinary galaxies. Okay, so how do we do that? There are different ways of doing it. Now, this is a unique thing, MCG 63015. Okay, so what this is a Seyfert active galaxy, and you have got you look at the X-ray emission from this galaxy. Okay, and then when you look at the X-ray, there is a feature there is a very bright line of iron. It's a very highly ionized state of iron, and which arises in the circumstances which you expect to find in active galaxies. And then when you look at the shape of the line, I mean you should get a Gaussian shape or whatever, you find this shape related to these two horns there. You appear to see these two horns. And so now if you have got emission coming from a rotating disk, then you expect this two horn shape as we see from elementary astronomy. But now if the emission is occurring very close to a rotating black hole, okay, then there are all kinds of effects which arise. Okay, there is the because of the fact that the photons are going round and round before they escape to you. So these effects lead to the complex shape of the galaxies. So if you indicate those shapes which are inherently general relativistic in nature, then you would say that yes, there is a black hole, and until then it just remains a dark compact object. Now here you might be too poor. Okay, so it's not, this is highly likely but not completely established yet. Okay, but there are other ways of doing it, and here for example you have got the Hubble Space Telescope observations of the internal part of the galaxy, and you see you see the spectrum red shifted on one side, blue shifted on the other. You know it's a rotating disk, and you can estimate the mass around which the disk is going. Then you can use the maser light coming from galaxies, you can do all sorts of things, but the most beautiful of all and the most convincing is the observation at the center of our galaxy itself. Right? So what happens there is that it's impossible to see stars at the center of a galaxy because it's about 8 kiloparsec away. You have to look at it through the disk of the galaxy, and there's immense absorption there. As a result of which, at visual wavelengths, you cannot see stars at the center of the galaxy. Right? And moreover, you require very high resolution. Now, this has become available over the last 15 years or so because of technology. And you're going to listen to a talk by Sri Kulkarni about what happens with new technology. And this is an amazing example of that because it combines new technology in terms of the measuring apparatus with the very classical approach of Kepler, okay, and to establish the mass of the object at the center. So what happens here is that now you are really gone to a very, very small part of the galaxy, look at it at near infrared wavelengths and adaptive optics and follow the orbit of stars. And you see that this particular star, the orbit has been followed from 1992 to 2002. Actually now it has been followed even further than that, so the orbit, you see the beautiful elliptical orbit here. And the Sagittarius A, which has that position has long been suspected to be the center of the galaxy in some ways, actually sits at one focus of this ellipse. And you can estimate the mass of the object there, and that turns out to be 4 into 10 to the 6 solar masses. Okay, I actually have the diagram with me where this orbit is closed, nearly closed. It's just not closed at that point there because of the precession. And it was too late last night to put that in. Okay, but so you see that you have got this point sitting here, and now the question, and the fact that the periastron distance is so small allows you to establish the fact that the object is extremely compact. Okay, and then the theory tells you that it could hardly be anything other than a supermassive black hole. So now these black holes have been these galaxies, and these are all in this table, which you need not look at the numbers. The fact is that there are 60, 70, 80 of them, and they're all ordinary galaxies. They're not active galaxies or anything. And a black hole, supermassive black hole mass measurement has been made using one technique or the other at the centers of all of them. And I just have got a few minutes left now. And what happens here is that the moment you get a catalog, you correlate whatever you can against anything else there, which is there. Okay, so and then you begin to find the patterns. These two emerge over a period of time, and in day after tomorrow's talk, talking about, or she'll be doing this thing about how these black holes are formed. I'm not touching on that aspect at all. So you find here that that the luminosity, that the mass of the black hole is correlated with the luminosity of the galaxy, but with much less scatter, the mass of the black hole is correlated with the dispersion velocity. So what it means is that the dispersion velocity can be measured for galaxies, and that allows you to predict the black hole mass. And what has been argued very hotly is exactly what is the slope of this one. And the slope depends not on the data, but on the method of data analysis. Okay, because that is what is very important. Is that, do I fit x against y, and do I fit y against x, and if I do both, then do I take the bisector? Is one question which we are asked when in our younger days. Now here this question is similar to that as to the exact way in which you do the analysis, the way in which you take care of the error bars, but that has a discernible effect on the interpretation that you put on the formation mechanisms. Right? So the kind of correlation that you get, and we have been trying our hand at it, trying to develop a fundamental plane out of these. And you see that here, again you are back to the familiar parameters. So you see that this is a set of galaxies for which the supermassive black hole mass is there, and what do we have here? We have the effective radius, sigma, and the brightness, so which means that this is simply the fundamental plane of these galaxies. Okay, so but now what do we do? So we just take away one of the parameters, take away sigma, and put in the black hole mass. Right? So then you get this very tight correlation. The only problem being that the number of points is quite small. Okay, so you get a much tighter correlation than the two-dimensional relationships. It is a direct correlation. It doesn't come out of first taking the fundamental plane, then relating sigma to m, and by turning the axis around and doing the refitting, it allows you to estimate black hole masses given the photometric parameters with about a 20% scatter. Okay, so this is an improvement over what is possible, except that it has not been very straightforward because of all the problems in gathering the data to extend this quickly to a much larger number of objects. And we have tried it from time to time, but the inhomogeneity of the data and the difficulty in trying to obtain much better data is not made that impossible. Okay, I'll stop there. Thank you very much.
So Ajit, early in your talk you showed this divocular profile for some galaxy, and then later you said that you could generalize it to search with 1 over n. My question is there a fundamental understanding of that profile? Does it come from any statistical mechanics argument or a distribution function?
No, I don't think so. To my knowledge, there is really no, let's say, basic explanation of the profile. It apparently turns up in various simulations and so on, but there is no straightforward reason why this simple profile should exist.
And yet it is so universal.
Oh, it's absolutely,
it's like really, I mean, interesting, basic, it's a statistical issue.
Yes.
How do we do a self-gravitating set of point masses?
Yes.
And what configuration would they take?
Probably, the hope is that the kind of correlation that I've been describing, okay, these would lead to some insight into. And if you see that the statistical parameters related to this and that, then it might, like for example, you might be able to take off from that and develop a model. Okay. Yeah. You also need good physicists. Okay.
We have them too.
So after this part, I mean, you had this lenticular galaxies which were of two types, and then the bright ones and not so bright ones. And you also pointed out that there is reason to believe that the formation mechanisms were different in the two cases.
Yes.
Now again, I mean, do we understand this? In fact, that in fact the formation mechanism was actually merger, then they should be Fenter, and the other formation mechanisms.
What happens is that, I mean, as you might imagine, the number of simulations available is not very large, and certain groups have been doing them. So what you will get references to these very specific papers over the years. Okay, so they would take galaxies of a certain kind and merge them together. But you don't have a whole spectrum of masses merging with another spectrum of masses because of the great difficulties in carrying out the simulations and interpreting the results. Right? So it appears that when there are major mergers, then you get these ellipticals, and then if there is a disk is formed, then you would also get these lenticulars. Okay, so and there sometimes you see this anti-correlation.
Can you see that those lenticulars then would be less bright than the other lenticulars, because that was you divide the population into two parts.
Yes, 2 parts, yeah.
Right. So therefore, and the less bright were the ones which were supposed to be obtained.
Yeah, the less
so
bright.
can one see, the simulations or modeling, does that explain that these should be less bright than the other ones?
You see, first of all, you have to see where the brightness comes. The brightness actually would probably come from the depth of the potential well. Okay, so you've got the L by M ratio, so that will lead to the brighter the galaxy, the greater is the mass which is involved in them. Okay, and so that will tell you how the seed things were in the beginning, right? Now, if you the thing about the bars is that you would not be able to carry out calculations there through n-body simulations because there's a gas dynamical problem. Okay, so there probably the difficulties because of that. But I mean, we have been we would like to get together with people who do such things. They're not happened for some reason or the other, but it's not easy because of the fact that the gas dynamics comes in.
You know, you made a remark that in the MCG 6 days, 30 days, 15, the latest line, which you see asymmetry, is large scatter, and therefore it is, not very sure. One is not sure whether it is really true. But actually, there has been a very detailed observation now with XMM Newton with much improved statistics, and shows a clear same trend.
Oh, the clear trend.
Okay. And also in stellar mass black hole now, at least half of a dozen of them, asymmetric lines similar to this has been seen.
Yes. Okay.
You mentioned that stars have different ages, because some are younger, some are older, and so on.
Yeah.
Also, qualitatively, that the bigger the star is, the shorter is life, and so on.
Yeah. Yes.
Is it possible that bigger stars undergo collapse and then trigger the collapse at the center? Is it possible?
Oh yes. You see, what would happen is that if you look at the first generation of stars in a galaxy, right? So then they would all collapse, and then they would form these black holes or neutron stars, and then if they have larger mass than the other, they could.
Massive black hole. That's
The one possibility is that you form a star cluster. Now, if the star cluster is very compact and very dense, there will be a lot of interactions between the stars. Now, as they explode and then they leave the remnants behind, those would also be gravitationally interacting with each other. Now, if you can transport the angular momentum out, then these will collapse to form a hole there. Okay, but maybe she can say something more about that, because. Yeah.
I'll be talking about it on great detail on Wednesday.
Yeah.
Various channels to form seed black holes.
Yeah. Because there are different channels by which you could form these black holes, and but once I knew that she was going to come here, I decided not to go into that at all. Thank you.